All right, so buckle up, everyone, because today we are going on a deep dive into the wild world of flight. You know those pages from 4phak.pdf you sent over? The ones that look like a pilot's secret handbook?
Yeah. Ugh.
No. We're going to break them down and figure out exactly how those massive hunks of metal manage to stay up in the air.
It's actually a pretty amazing blend of physics and engineering, and the best part is you don't actually have to be a pilot to wrap your head around it.
Well, that's good news for me.
Hmm.
So where do we even begin with this? Do we start with those giant wings? Or maybe the engines? Please tell me time travel isn't involved.
As fun as time travel would be, we'll be starting with something a little bit closer to home, the atmosphere itself. It's not just empty space up there.
Well, yeah, because if it were, those trips to space would be a lot shorter
Yeah.
and probably way more terrifying.
Exactly. And when we're talking about flight, the atmosphere is way more than just a backdrop. Its composition plays a huge role in how planes fly. I mean, we all know air has oxygen, right? We kind of need that to breathe. But get this, the atmosphere is mostly nitrogen, like a whopping 78%. Oxygen only comes in at about 21%.
Wait, seriously? I always thought, oxygen was the main ingredient in the atmosphere.
Right? It's a super common misconception. I get that. But think about it this way. Nitrogen, it's actually a much lighter gas than oxygen, right?
Yeah, I think I remember that from chemistry class. Maybe.
So because of that, heavier oxygen actually tends to settle closer to the Earth's surface.
It's
Kind
fair.
of like, how it gets a little hard to breathe when you go up really high? Like above 35,000 feet, you need a little help to breathe comfortably?
Okay, that makes sense.
Hmm.
So the lighter gases are floating higher up, and the heavier ones are chilling down here with us.
Yeah.
It's like oil and water in a salad dressing, right?
You got it.
Speaking of fluids, we got to talk about how air, even though we can't see it, acts like a fluid, right?
You're totally right. Air, it might be way less dense than, say, like water, but it flows and it has viscosity, just like any other fluid.
Okay, hold on. Viscosity. That's just a fancy way of saying how much a fluid, resists flowing, right?
Yeah, exactly.
So thicker fluids have higher viscosity, and thinner fluids have lower viscosity. Can you give me a real-world example? Because that all sounds a bit too much like a textbook for me.
Okay, so picture this. You've got honey and a glass of water, right? Which one flows more easily?
Water, obviously.
Exactly. Water is low viscosity. Honey, on the other hand, honey's thicker, takes its sweet time flowing. That's high viscosity. Air, as invisible as it is, acts the same way.
Okay, I'm with you. So a plane flying through, thicker, more viscous air that would be kind of like trying to swim through a pool of honey. Not very efficient.
You got it. And that's exactly why understanding things like air density is super crucial for flight. But before we get too far into that, we've got to talk about another key player. Atmospheric pressure.
Okay, let's unpack this whole pressure thing. And we're not talking about the pressure of trying to snag that last-minute upgrade to first class, right?
No, although that's a whole different kind of pressure, isn't it?
Tell me about it.
No, we're talking about the weight of all that air above us pushing down.
So, the higher you go, the less air there is above you, so less pressure.
Exactly. And that's where the concept of standard atmospheric pressure comes in.
Standard atmospheric pressure. Hit me with it.
It's basically a baseline measurement that gives pilots a way to understand how the atmosphere is behaving on any given day. Like a reference point.
So is that kind of like, how our source material mentioned that standard atmospheric pressure at sea level is 29.92 inches of mercury?
Yep.
That seems awfully specific. Is that something pilots actually use?
They do, but think of it less like, a ruler and more like if you were looking at a barometer, those classic instruments with a column of mercury.
Oh, yeah, okay.
So at sea level, under standard conditions, the atmosphere is pushing that mercury up to about 29.92 inches. And that's just another way of saying 1,013 millibars, just a different unit of pressure.
Okay, so 29.92 inches of mercury. Got it. Starting to see how all these measurements fit together. But how does temperature play into all this? Because it gets pretty chilly up there at 30,000 feet, right?
Oh, yeah, it definitely does get cold. And you know what? That temperature difference, it's actually directly related to pressure and altitude. So basically, for every 1,000 feet you go up, the temperature drops by about 2 degrees Celsius.
Wow. 2 degrees for every 1,000 feet. No wonder it's freezing up there.
Right. And it's not just the temperature. The pressure also decreases at a rate of about 1 inch of mercury for every 1,000 feet you climb.
Okay, so lower pressure, lower temperature. Is that essentially what creates that thinner air we were talking about earlier?
You're getting warmer, literally.
Huh. So if the temperature and pressure are constantly changing with altitude, how do pilots keep up with that when they're flying? It can't just be a guessing game, right?
Right. Oh, absolutely not. It's definitely not a guessing game. That's where the super interesting world of density altitude comes in. It's a calculation that takes all those factors we've been talking about into account.
Hold on, another type of altitude.
Hmm.
We're talking about something more than just how high a plane is flying.
You got it. So density altitude, it's like pressure altitude, but with a twist. It takes things like temperature and even humidity into account to give pilots a more realistic picture of how the aircraft is actually going to perform at a specific altitude. It's almost like you could call it performance altitude, maybe.
Okay, this sounds crucial. I'm ready to dive deeper into this whole density altitude thing.
Yeah.
How does it actually work? And why should I, as a non-pilot, care?
All right, so let's say you're at an airport, right? And the pressure altitude is, let's say, a respectable 8,000 feet.
Right.
But it's a scorcher of a day, 80 degrees Fahrenheit, super humid, like 75% humidity, that sticky kind of heat. Suddenly, that 8,000-foot pressure altitude, it translates to a density altitude that's closer to 11,564 feet.
Whoa, wait. That's over 3,500 feet higher, just because of the temperature and humidity.
Exactly. And what that means is the aircraft is going to perform as if it were at that much higher of an altitude. Thinner air. That means less lift, less power from the engines, and it means you need a longer runway for both takeoff and landing.
Wow, I never even realized. So density altitude is really all about understanding how those atmospheric conditions impact how an aircraft actually performs, not just where it is in the air.
You nailed it. It's a super important concept for pilots to be aware of, especially during takeoff and landing when safety is, paramount.
Seriously, this is blowing my mind. So we've covered the atmosphere, pressure, and now this whole density altitude concept. I'm starting to get a feel for all those invisible forces at play here, but we still haven't even touched on the big question. How do those giant metal birds defy gravity and stay up in the air?
Well, the answer lies in a pretty brilliant combo of, like I said, physics and engineering, specifically the shape of the wing and a little something called lift.
Okay, all right, you've teased it enough. Let's talk lift.
Okay, so we've talked about how air density is a big deal and how pilots use this thing called density altitude to get a real-time feel for how a plane is going to behave up in the air. But how does all this tie into the force that's actually counteracting gravity? The thing keeping those planes uplift.
That is the million-dollar question, isn't it?
Pretty much.
And you know what? The answer is this super cool interplay between the shape of the wing, the angle of attack, and some pretty basic physics.
Okay, hit me with those physics. I'm ready for my crash course in aeronautics.
All right, so the easiest way to think about lift is this. It's all about the difference in air pressure between the top of the wing and the bottom.
So, the wing is basically a pressure sandwich with higher pressure underneath, kind of pushing it up.
You're getting there,
Yeah.
but it's a little more nuanced than just that. It's actually the specific shape of the wing, the airfoil, that really makes the magic happen.
Ah, yes, the airfoil, that classic teardrop shape you always see in diagrams. It's like the universal symbol for airplane wing. Exactly. And that shape, curved on the top and flatter underneath, it's specifically designed that way to kind of manipulate the airflow.
Manipulated how?
Let me ask you this. Have you ever wondered why, when you turn the shower on full blast, it feels like the shower curtain gets sucked in towards you?
Oh my gosh, all the time. I always thought it was like some weird bathroom gremlin or something.
It's actually a perfect real-world example of something called Bernoulli's principle.
Bernoulli. Okay, I think things are about to get sciencey.
Don't worry, it's really not that complicated. Bernoulli's principle basically just says that when a fluid, in this case, air speeds up, its pressure actually goes down.
Okay, so faster air equals lower pressure.
Hmm.
But how does that relate back to my shower curtain gremlins?
So when that shower is on full blast, the water creates this column of really fast-moving air.
Right.
And that fast-moving air, well, it has lower pressure than the still air just outside the shower. And you
Ah.
know what happens when you have a difference in pressure? Things move from high pressure to low pressure. So the air, or in this case your shower curtain, it's trying to move towards that area of lower pressure, hence getting sucked in.
Mind blow. So you're saying my shower curtain is like a tiny airplane wing.
In a way, yeah. Just like with that shower curtain, the shape of the airfoil on a plane's wing is designed to play with this concept of pressure. The air flowing over the top of the wing, the curved part, it has to travel a longer distance in the same amount of time as the air flowing underneath, which has a much shorter trip.
Okay, so the air on top is moving faster, which, according to Bernoulli, means...
Lower pressure. You got it. So you've got this area of lower pressure on top of the wing and higher pressure underneath, and boom, you've got lift.
Ooh. Okay, that makes sense. But you also mentioned Newton's third law earlier. Where does that come into play?
Ah, yes, Newton. Good old, for every action, there is an equal and opposite reaction.
I vaguely remember that from high school physics. Remind me.
All right, so imagine this. You're on a skateboard, right?
Okay.
And you throw a basketball forward.
Yeah.
What happens?
I mean, hopefully someone catches it.
Sure, but what happens to you?
Oh, I move backward.
Exactly. The force you put on the ball, throwing it forward, it creates an equal and opposite force that pushes back on you.
Okay, got it. So how is an airplane throwing air to stay up?
It all comes down to something called the angle of attack. It's basically the angle at which the wing hits the oncoming air.
So the steeper the angle, the more air gets pushed down.
You got it. As the air flows over the wing, it's not just going over and under, it's also being pushed downwards. It's being deflected. And just like with your basketball on a skateboard, that downward push on the air creates an upward force lift.
Wow. So it's like the wing is constantly pushing down on the air, and the air is pushing back, keeping the plane afloat.
You got it. It's this beautiful dance between Bernoulli's principle and Newton's third law that makes flight possible. Of course, this is all happening with a little help from a thrust from the engines to move the plane forward.
It's all making so much sense now. So more speed, more angle of attack, more lift, right?
Well, to a certain extent, yes. But there's always a trade-off. Increasing the angle of attack too much, you do get more lift, but it also creates something called drag.
Drag.
Yeah, it's basically the aerodynamic force that tries to slow the plane down, like air resistance.
Ah, so it's like friction, but for the air.
Exactly. And too much drag, it can slow the plane down and make it a lot less efficient. That's why you see engineers and designers constantly working to make planes more aerodynamic. With those sleek designs and smooth surfaces, they're trying to reduce that drag.
So it's like this constant balancing act between getting enough lift without creating too much drag.
Exactly. It's all about finding that sweet spot. Oh, and remember that downwash we talked about earlier?
The not detergent kind.
Yes. That downward flow of air behind the wing, it can actually create drag and make the wing less efficient. And this is where things get even cooler. Engineers, they realized this was a thing, so they designed those little wingtip things you see on some planes. You know, those winglets?
No way. Those actually do something. I always thought they were just like decorative, to look cool.
They are definitely aesthetically pleasing.
They are?
But they are totally functional, too. They help to reduce the intensity of those little swirls of air, those wingtip vortices. They redirect that airflow in a more vertical direction. This makes the plane more fuel efficient, and it reduces drag overall.
This is amazing. Who knew there was so much science behind those little winglets? Okay, so we've covered a lot of ground here, from the atmosphere and air pressure to Bernoulli, Newton, even shower curtain gremlins. But before we go too far, I've got a question. Is this like the same principle that lets helicopters fly? Because they don't have those classic airfoil wings, do they?
That is a fantastic question, and you've hit on a really common misconception. You see, while both planes and helicopters, they need lift to stay up in the air, the way they generate that lift is actually completely different.
So we spent all this time talking about how planes use their wings and all those principles of lift to stay up in the air. But what about helicopters? They don't have those big fixed wings. How do they manage to, take off vertically and even just hover in place?
You're absolutely right. Helicopters, they go about generating lift in a totally different way, even though the basic idea, that pressure difference, it's still at the heart of it all.
Well,
Instead of using fixed wings, helicopters use those rotating blades, which are kind of like spinning airfoils.
spinning airfoils. Okay, you're going to have to break that one down for me.
Okay, so picture those long, slender blades you see on top of a helicopter, right?
Right.
As they spin, they cut through the air at a specific angle, just like a plane's wing would. This creates that same pressure difference we were talking about before. Lower pressure above the blade, higher pressure below, and that's what gives them lift.
So even though the blades are spinning, those same aerodynamic principles we talked about earlier still apply.
Exactly. Bernoulli and Newton, they're still hard at work, even in a helicopter. The really cool thing about a helicopter's design is that the pilot can actually control the angle of attack of those spinning blades, which means they control how much lift is being generated.
Ah, okay, so that's how they can take off vertically then, by generating enough lift to overcome their own weight.
Exactly. And by making tiny adjustments to the pitch of the blades, that's basically the angle at which they're tilted, the pilot can really fine-tune the direction and the intensity of the lift, which is how they move forward, backwards, sideways, or even just hover in place.
Wow, that's incredible. It's like the pilot is conducting an orchestra of air with those spinning blades. So While airplanes are designed for like speed and efficiency in forward flight, helicopters, they're all about maneuverability and that really precise control.
Absolutely. And it's that fundamental difference in how they generate lift that gives each aircraft its own, like, unique set of strengths.
This whole deep dive has been seriously eye-opening. We've covered so much, from the basic makeup of the atmosphere to understanding those invisible forces that allow both planes and helicopters to do their thing. I feel like I've earned my wings, or at least like honorary wings.
Well, I'd say you've got a much better grasp on the fundamentals of flight now than you did before we started.
Definitely. So for everyone listening, if you, like me, haven't really thought much about the science that makes flight possible, I hope this deep dive has inspired you to maybe look up at that next plane or helicopter with a new sense of awe.
I completely agree. Never stop questioning, exploring, and just looking for those aha moments in the world around you. After all, that's what this deep dive is really all about.